let's take a look at how you're doing with these so far. Some of you may not be done with them, and that's fine. The first one, 4 3/8 minus 2 5/6. I'm going to write it vertically just because that's how my mind does addition and subtraction. We need to find a common denominator, which is going to be what? 24. Good. So 3/8, what's this number up here going to become? 9. There we go. 8 times 3, so 3 times 3. What's this one here going to become? 20. Perfect. 6 times 4, so 5 times 4. So now we go to subtract. 9 minus 20 doesn't work, so we're going to have to borrow. So this is going to become 3. What do we add to the 9? We add the denominator, 24. Good. So we get 33 there. And now when we subtract, 33 minus 20 is 13 24. So we keep the same name. 3 minus 2 is 1. Number 2, to multiply fractions. Remember, for mixed numbers, we said rather than doing the difficult process of multiplying the mixed numbers, we turn them into improper fractions. So to review that, to turn 3.5 into an improper fraction, where our denominator won't change, that's always going to stay the same. That's going to be 3 times 2 is 6, plus 1 is 7. So that's 7 halves. We're breaking that whole number up into pieces by multiplying it by the denominator. So for the 2 4/5, again, the denominator is going to stay 5. 2 times 5 is 10, plus 4 is 14. And now we are multiplying, so we can cross cancel. On the diagonal there, both 2 and 14 can be divided by 2. 2 divided by 2 is 1, and 14 divided by 2 is 7. Now 7 times 7 is 49. 1 times 5 is 5. And now we have the task of trying to reduce that into a mixed number. So it's just a division and a remainder. 49 divided by 5. 5 goes into 49. Hello. 9 times 5 is 45. There's 4 left over. So that is 9 4/5. How many have both of them right so far? Show of hands. Didn't get to the second one? Okay. Number 3, to do division. If we recall, to divide fractions, we are going to turn it into multiplication by finding the reciprocal of the number we are dividing by. So if we're going to turn it into multiplication, we'll do the same thing we did for multiplication, which is make improper fractions. So this is going to stay thirds. 5 2/3 becomes 17. Good. 5 times 3 is 15 plus 2. We're still division at this point. 1 5/6 will become 11. 1 times 6 is 6, plus 5 is 11. And again, note the denominators stay the same. Now the division operates on the number that comes after it, which is the 11/6. So our 17 over 3 will not change. It's going to become times the reciprocal of 11/6, will be 6/11. And then we're going to cross cancel the 3 and 6. Both divided by 3. 3 divided by 3 is 1. 6 divided by 3 is 2. 17 times 2 is 34. 1 times 11 is 11. And we have to reduce that back down. 34 divided by 11. 11 goes into 34 3 times. 3 times 11 is 33, so there's 1 left over. So there's 3 and 1/11. Any questions there? Yeah? The whole thing? Okay. So just like when we did the multiplication here, we had to turn it into improper fractions. So we did that part. Now when we multiply, there's a whole series of steps we could do. But remember, we chose to take that process of just multiplying by the reciprocal. Remember, we had 3/4 divided by 2/3. Instead of dividing by 2/3, it's the same if we multiply by 3/2. So we take that reciprocal. So that's what we did here. Instead of dividing by 11/6, we change it to times 6/11. And then we multiply. Now, since it's multiplication, we can do that cross reduction or cross canceling. So we have the 3 and the 6 here that both can be divided by 3. So we divided that out. 3 divided by 3 gave us 1. 6 divided by 3 gives us 2. And so now when we multiply, it is 17 times 2 gives us the 34. And 1 times 11 gives us the 11. Yep. After we've done the reciprocal. Some people were taught that when you divide, you do something. It's called the zigzag method. So, but that would give you the same result. But what it is, I think it's kind of confusing. You do 17 times 6 was like 102, and 3 times 11 is 33. And then you have to reduce that. And it will reduce to 34/11 or 3 1/11. But I think that zigzag is just a gimmick to avoid having to take the reciprocal. Number 4, back to adding again. 3 1/2 plus 7/8. There is no whole number on the 7/8, but it doesn't change anything. What's our common denominator going to be? 8. So the 7/8 stays as 7/8. 1/2 is going to become 4/8. Now when we add, 4 plus 7 is 11/8. Now that's bigger than 1. So if we take 1 out of there, how many pieces are left over? 3. 11 minus 8 is 3. So there's 3/8 left over. So we keep the fraction portion, we keep the 3/8, and we carry the 1. And 1 plus 3 is 4. So 4 3/8. Any questions there? Okay. So last class, we talked about that count in the name and the place values a little bit. And we looked at, a number like 384 and realized that that's really 3 hundreds and 8 tens and 4 ones. But we're going to look at those place values a little bit more closely here for a second. Remember we said this is the ones place, the tens place, the hundreds place, 1,000s, 10,000s, and so on. That's right, that's the way I've got it. Nope, the ones place is always at the end of the number. You're thinking going the other way. This would be the 1/10ths and the 100ths and so on. If you're going decimal places after the decimal, this is the 1/10ths, the 100ths. This is before the decimal, the whole number part. Yep. No problem. If we look at powers, like 10 to the power of 3, what does that equal? 1,000, right? 10 times 10 times 10. 10 to the power of 5. 100,000. Do you guys remember the shortcut for doing powers of 10? Whatever the power is, is how many zeros are on the end of it. There we go. So 10 to the 4th is a 1 followed by 4 zeros. So if we come back here and look at our place values, 100 is just 10 squared, 10 to the power of 2. 1,000 is 10 to the power of 3. 10,000 is 10 to the power of 4. 100,000 is 10 to the power of 5. How about just 10? It's 10 to the power of 1. Anything to the power of 1 is just itself. Any number we write, if we just write a digit like 7, that's implied to be 7 to the power of 1. We just don't write that power in. 10 to the power of 0. Because 5, 4, 3, 2, 1, the pattern would continue. That'd be 10 to the 0. Anything to the power of 0 is equal to 1. Now, in this class, we don't stress a lot of like 0 powers and negative powers. We'll look at them a little bit maybe at these decimal places, maybe next week if we have time to touch on scientific notation. But if this were like a tech math or a college algebra class, we would look at those powers of 0 and negative powers quite a bit. And what it really comes from is just the pattern. 10 to the 3rd is 1,000. 10 to the 2nd is 100. 10 to the 1st is 10. Every time we reduce that power by 1, we're dividing by 10 here, correct? If I reduce it again to 10 to the 0, what's 10 divided by 10? 1. Anything to the power of 0 is 1. In fact, you can do it on the calculator if you want to. You can do 58 to the power of 0. It gives you 1. Which, by the way, has led to me having a lot of fun with students in the past. It doesn't work out in this class. Like I said, that's not the focus of this class. But I've had tech math classes where I've done things like this. What's that equal? 1. Well, like I said, that's not the focus of this class, so I wouldn't do that. But anything to the power of 0 equals 1. Like I said, I won't do that to you guys. This class meets late at night, and I do like to be able to walk to my car without having to listen for revving engines for too long. That way. It's a brown Cutlass. That's actually my boss's car. But anyway, back to these place values. So instead of writing out the word hundreds, tens, and ones, instead of writing out 3 hundreds, 8 tens, and 4 ones, what we could have done is 3 times 10 to the 2nd. That's the hundreds place. Plus 8 times, we don't have to write the 10 to the 1. We can just write times 10. And plus 4, we don't write in the ones or the 10 to the 0. When we write a whole number that way, and that's just representing the 384, we see some correspondence with our algebraic numbers. Our algebraic numbers might look like this. Here we can see this algebraic number is really just a number written out in long form, where the place values aren't powers of tens anymore, they are powers of x. This is the ones place, or the x to the 0. This is the x to the 1, or just the x place, and the x squared place. Because of that, we can work with these algebraic numbers exactly like we work with our whole numbers. So let's talk a little bit before we get too deep into this. What does that x mean there? What is a variable? That variable, that letter, is just representing some missing value. Could be a number, could be some other form of a value, but it is just a value. And it can be done in a couple of different ways. It can be a generic representation. This is usually to form a rule. An example of this might be, a rule in math is if you're adding two numbers, the order doesn't matter. So you say A plus B is equal to B plus A. So in that case, those variables, A and B, are variables. They are representing any possible number you could put in there. Yeah, no, whatever number you pick for A has to go in here as well. Whatever number you pick for B has to go there as well. Yes. It can also represent formulas. In this class, we are going to use a lot of these. An example might be interest is equal to principal times rate times time. Now, in this case, they could be any possible number within a reasonable range. What they're doing is they're waiting for a value. Up here, we don't care what their values is. It's expressing a rule. The symbols are really all that needs to be stated there. Down here, each of these are waiting for a value to be given to them. So at some point, we might say that the principal P is equal to $5,000, and that R is equal to whatever percent we're going to put in there, and T is equal to so many years. They're waiting for values to be given to them, and once we give them values, we can calculate the missing pieces. We're going to use a lot of them in that form in this class. The whole third unit of this class is formulas. And finally, it is an unknown value where it has a specific value. We just don't know what it is yet, but we can find it. And that'll come in equations like this. 3x plus 2 equals 23. Here, x has only one value. And we can go ahead and proceed to figure out what that value is. We'll talk about those later on in class tonight. So for now, let's go back to those algebraic numbers we had up above and look at how do we work with those. 5x squared plus 7x plus 3. Remember, last week when we talked about whole numbers and fractions and decimals, we came up with rules for adding and subtracting. When we add and subtract numbers, there are two big conditions. One is we need the same name. This took a lot of forms. In fractions, it meant we had to have a common denominator to add them. For whole numbers, it meant that we could only add digits that have the same place value. That's why we had to line up the columns, so we're only combining ones with other ones, and tens with other tens, and hundreds with other hundreds. The second thing, we're going to combine the counts, but when we add and subtract, we keep the same name. So for our fractions, we combine the counts, 2 plus 3 is 5, but we kept the same name as sevenths. Whole numbers, we added down the column, 5 plus 2 is 7, that stays in the ones digit. 7 plus 1 is 8, that stays in the tens digit. And 2 plus 5 is 7, which stays in the hundreds digit. So with our algebraic numbers, those same rules apply. (5x plus 12x), what's that going to become? 17x, very good. 3x plus 8y, what's that going to become? 3x plus 8y. Those have different names, we cannot combine them. However, we can run into things like this. Looking at that, there are different names. There's A's and B's, but there are some that are the same. So that means we can combine 5a with 3a. Now remember, we said the operation goes with the number that comes after it. This is addition here that goes with the 3a. That's telling us that is a positive 3a. So 5a, positive 5a, and positive 3a make 8a. Plus 7a means it's positive 7a, plus 6, or positive 7b, I should say. Plus 6b is a positive 6b, so those combine to make positive 13b. So since it's positive, I put a plus in front of it. We can have things like this. So when we go to combine here, we've got 3x, and what can we combine with it? Positive 7x. That combines to make 10x. It's positive, but we don't need to put a plus in front of it since it's the first number. Negative 9y and positive 4y is a negative 5y. So that negative becomes a minus in front of the 5y. That is it right there. It would be perfectly acceptable to write it as 10x plus a negative 5y. Those two mean exactly the same thing. Remember, subtracting and plus a negative are the same thing. You could put parentheses around that. So let's keep going with that to a little bit more complex numbers, like 5x squared plus 3x plus 9. Let's add that to another algebraic number. Now, just to clarify, I put parentheses around that. That's not telling us to do anything there first. And when we talk about order of operations, parentheses usually tell us we have to do something there first if they're used as an enclosing symbol. Here, it's not an enclosing symbol. It's just separating like we did with negatives, specifying that that is a single number. Plus 3x squared plus 5x plus 7. Just like with whole numbers, when we did addition, we lined them up so that the place values are lined up. We're going to do the same thing here. So I'm going to rewrite that first number, 5x squared plus 3x plus 9. Now for my second number, the 3x squared goes with the 5x squared. The 5x goes with the 3x. And the 7 ones goes with the 9 ones. And we are adding. So we're just going to add down the columns. What's 9 plus 7? 16, and it's positive, so there's a plus there. 3x plus 5x. 8x, positive again, so we're going to put a plus in front of it. And 5x plus 3x, or 8x squared. 5x squared plus 3x squared is 8x squared. That's the first number, and it's positive, so I don't need anything in front of that. So that's it. Now, I should note that many of you were taught when you're adding algebraic numbers, this term that sometimes uses polynomials, that all you have to do is take out the parentheses and combine the like terms. And that's fine if that's the way you were taught how to do it and you like doing it that way. I'm okay with that. Notice you're still going to be combining the same things. To me, it just makes more sense if you're going to be combining them to line them up and add them in columns just like you do with whole numbers. We've already seen here one of the difference between our algebraic numbers and whole numbers. In a whole number, we can't have two a two-digit value and a place value, we couldn't have 16. We'd have to carry. In algebraic numbers, we don't ever carry. We could have as many digits in each place value as we want. The other big difference is our negatives. If I have a number like 387, let's make it a negative 387. Either every digit is positive or every digit is negative. So since that's negative, that's a negative 300s and a negative 8 tens and a negative 7 ones. With an algebraic number, it's possible for each digit to be positive or negative on its own. Every digit of the number does not have to be the same sign. So we might have 5x squared minus 9x plus 2, where you can see that second digit's negative, but the other ones are positive. And let's add that to 2x squared plus 5x minus 13. And we would still go ahead and just line them up like we do whole numbers. We'll rewrite that first one, 5x squared minus 9x plus 2, 2x squared plus 5x minus 13, and we're adding. And here's where those negatives can give us a little bit of a struggle. Positive 2 plus negative 13. Negative 11. Very good. Think of it as the number line. 0, you go up 2 and back 13. It's negative 11. Negative 9 plus 5. That's negative 4. So it's a negative 4x. Good. And 5x squared plus 2x squared? 7x squared. And there it is. Any questions? Subtraction. Works very similar to addition. We're going to rewrite the first number. Then we're going to line up the place values on the second number. X squareds under the x squareds, x's under the x's, ones under the ones. And we're subtracting now down the columns. What's 4 minus 7? Negative 3. How about 12x minus 3x? Positive 9x. Good. 3x squared minus 5x squared? They have 2x squared. There you go. I know what you meant. So, now again, if we have digits in there that are negative, it can get, oh, by the way, side note, many of you, again, were probably taught when you go to subtract here, you can take out the parentheses of the first one, you can change this to addition and then change the sign of every number inside there, and then just combine like terms again. Again, if that's the way you were taught how to do it, I'm fine with that. That's just a shortcut for this longer process. So let's say we have 5x squared minus 7x plus 4 minus 3x squared plus 11x minus 8. So let's write this out again. Lining up the x squared with the x squared, the x's with the x's, ones with the ones, and we are subtracting down the column. 4 minus a negative 8 is a positive 12. Negative 7 minus 11, you think is a negative 7 plus a negative 11, negative 18. 5 minus 3, 2x squared. Either at the end of class tonight or sometime during class tomorrow, we'll talk about those negatives a little bit more. The negatives do take some practice. Yep. Yeah, it's 4 minus a negative 8. And when we subtract, technically, yeah, subtraction means add the opposite. So instead of 4 minus a negative 8, you change it to 4. This becomes plus. The opposite of this is a positive 8. Any questions? Yeah, negative 7 minus 11 becomes negative 7 plus a negative 11. Now 5 minus 3, we know how to do that one, so we don't have to change it. You could change it to 5 plus a negative 3, but to me that one's easier, is just 5 minus 3, because it's all positives at that point. You bet. Multiplication. What's 3x times 7x? 21x squared. When we multiply, we combine counts. But we also combine the names. X times x gives us x squared. Remember, when we multiply or divide, we do not need the same name. We're going to combine the counts as always, but we're going to also combine names. So that's why x and x become x squared instead of staying x. We could have 5x times 9y, and we're going to get perfect. Combining the counts, 5 times 9 is 45. Also combining the names, x times y is xy. Little talk about those powers. If we have a y squared, of course, that means y times y, right? Squared means 2 of them multiplied together. Or y to the 5th means 5 of them multiplied together. So what if I have y squared times y to the 5th? Well, that's 2 y's multiplied together. And this is 5 y's multiplied together. If I multiply them all together, what do I have? I have 7 of them, y to the 7th. The appearance is you add the powers, yes. This is what's called an exponent, the whole thing. And an exponent has 2 parts. It has a base, which is the bottom number, in this case the y, and it has the power. When we have the same base, which we do here, both of those are y, when we multiply exponents that have the same base, we just add the powers. 2 plus 5 gives us 7. So it's y to the 7th. So x to the 5th times x to the 12th would be x to the 17th. Good. How about if we're dividing them? That's only multiplication that we add the powers, yes. There you go. X to the 5th is 5 x's multiplied together. X to the 3rd is 3 x's multiplied together. If we look at what we did with the fractions, we can cancel out or can divide out. We can reduce it by dividing both the numerator and denominator by an x. We can do it again and one more time, and we are left with x squared. On bottom, all the x's are canceled out. Technically, it's x squared over 1, which is just x squared. And you had it over there. The shortcut, when we're dividing exponents that have the same base, both of these are x's, we can subtract the powers. 5 minus 3 is 2, so it is x squared. So if I have y to the 19th divided by y to the 5th, I'm going to get y to the 14th. Very good. So now we can combine it together a little bit here. 5x to the 3rd times 8x squared. We're going to combine the counts. What is 5 times 8? 40. And then we're also combining the names. X to the 3rd times x squared. X to the 5th. If we have more than one name, we can do the same thing. We might have 7x squared y to the 5th times 4x to the 4th y. We multiply the count. 7 times 4, 28. And then we can do each name separately. X squared times x to the 4th, x to the 6th. 2 plus 4 is 6. Y to the 5th times y. Well, just y by itself has what power? 1. Even though it's not written there, it's 1. So 5 plus 1 is 6. That's also y to the 6th. Well, what if we have a single digit number times a multiple digit number like this? This is just like having like 4 times 21. If we had this multiplication with our whole numbers, we would write the number with the most digits on top and multiply. 4 times 1 is 4. 4 times 2 is 8. Look familiar? We can do the same thing here. The number with the most digits is the 5x plus 2. Put the 3 on bottom and multiply. What's 3 times 2? 6. It's a positive 6, so put a plus there. 3 times 5x? 15x. So it's 15x plus 6. That is the long way to multiply those out. Now this is something that comes up often enough that even I'm going to go to the shortcut on it. Most of you, if you saw this before in an algebra class, were taught to do something called distribute. Distributing is just a shortcut for doing this process without having to write it out. It's just the rainbows. 3 times 5x would be 15x. 3 times 2, positive 6, so plus 6. Notice it's the same answer we got here. It just took less space. We might have 7x squared times 5x minus 8. Let's just go ahead. 7x squared times 5x. 35x to the 3rd, good. And 7x squared times negative 8. Negative 56x squared. Something like this. A 2-digit number times another 2-digit number. Again, we can treat it just like we would with whole numbers. With whole numbers, if I had 32 times 53. I have to do the 3 times 2, then the 3 times 3, and then move over, right? I can do the same thing here. I have 3x plus 2 times 5x minus 3. I do negative 3 times 2 is negative 6. Negative 3 times 3x, negative 9x. Now, we were always taught when we move over to the next digit, we got to leave a blank or put a 0 in here. I'm just going to leave it blank. 5x times 2, positive 10x. Notice that ends up under the other x's. 5x times 3x, 15x squared. And we can go ahead and combine or add down our columns. We've got the negative 6, negative 9x, and positive 10x. Positive 1x, or just x, and 15x squared. That is actually the full way, the long way of multiplying out those algebraic numbers. Most of you were probably taught a shortcut called FOIL. What's the F stand for? First. Multiply the first digit of each number. 3x times 5x is 15x squared. Notice that was down here. The O stands for outside or outer. 3x times negative 3, negative 9x. I stands for inside or inner. 2 times 5x, 10x. And the L stands for last. 2 times negative 3, negative 6. We notice we can combine negative 9x and positive 10x, which makes 1x, or just x. So it's 15x squared plus x minus 6. Same answer we got before. Just a little bit quicker that way. Now for business math, that FOIL process, multiplying out multiple digit numbers, isn't horribly useful. So we're not going to do a lot of it. But if you go on to a 4-year degree of any sort, you will go into a college algebra class. You will see that. I want to talk quickly about dividing before we hit our break time here. Let's say I have 18x to the third divided by 6x. Just like with multiplication, we combine the counts. What's 18 divided by 6? 3, and then we divide the names. That's really x to the 1. So x to the third divided by x to the 1 is x squared. 3 minus 1 is 2. We could have multiple names. We could have 144 x to the 5th, y to the 8th, divided by 9 x, y to the 7th. We divide the counts. What's 144 divided by 9? 16? Perfect. X to the 5th divided by x. X to the 4th. Good. Remember to treat that as 1. 5 minus 1 is 4. X to the 4th. Y to the 8th divided by y to the 7th. Y to the 1, or just y. Any questions? Okay. It is time for our break. We're like half a minute early, but 6:19. Let's come back at 6:29. Okay, so what we're going to look at in the second hour here is things that look like this. X equals 7. It's called an equation. And the heart of the key to understanding these equations is that symbol right there, which of course is called what? The equals sign, yes. Now here's the tougher question. What does it mean? It's kind of tough to define it without using the word equals, doesn't it? Same as? The same value. it means what's on one side of it, the x, has exactly the same value as what's on the other side of it, the 7. In fact, you can actually think of it like a balanced scale that balances about that equal sign. What's on one side exactly balances what's on the other. Now, all equations that ever existed start out in this form, as a variable equals a number. And they're actually built from there. Building equations, we can actually do any of our basic operations. We have add, subtract, multiply, divide. There are other operations we have. We have powers, roots, exponents, logarithms, trig functions, all sorts of things we can do. For this class, we're going to focus on these 6. So if I go to build onto this equation with one of those functions, let's take addition first. Let's say I want to add 5. So I add 5 to the x. X plus 5 is simply x plus 5. Now this scale is going to tip unless I do what? Not subtract, but add 5 to the other side. I have to do exactly the same thing to both sides. I added 5 to the x to make it x plus 5. I have to add 5 to the 7 to make it 12. Now that equation should still balance. Now, most of the time when we're working with equations, we're not really being asked to build the equation. We're being asked to solve. When we're asked to solve an equation, what it's asking us to do is take that equation apart and get it back to this form as a variable equals a number. Well, this equation was built by adding 5. How would we take it apart? Yeah, the opposite of adding is subtracting. So we subtract 5, and it removes that piece, leaving us with just x. But to keep the scale balanced, what do we have to do? There you go, subtract 5 from the other side. 12 minus 5 is 7. We're now back to that form of x equals 7, or variable equals a number. Now this example wasn't really fair because we built the equation, so we knew exactly how to take it back apart. The tough part about solving an equation is looking at it and figuring out how it was built. So let's take a look at some examples. Here, 3 is equal to y minus 9. Now to figure out how it was built, what we do is we find our equal sign, and then we focus on the side of the equation that has our variable on it. In this case, that's y minus 9. And now we ask ourselves 2 questions. One is, what is keeping our variable, in this case y, what is keeping y from being alone by itself on that side of the equation? Well, it would be the number 9. The 9 is keeping the y from being itself. Second equation, what operation was used to attach it? So the 9 is keeping y from being alone. What operation was used to attach that 9 to the y? It was subtracted. So this equation was built by subtracting 9. How do we take it apart? The opposite of subtracting 9 is adding 9. We add 9 to remove that, leaves us with y, making sure that we keep it balanced by adding 9 to the other side as well. 3 plus 9 is 12. So we're down to that form of a variable equals a number or a number equals a variable. At this point, if we weren't sure, we can double check it. You go back to this original equation, 3 equals y minus 9. And we can replace this number for the y. So instead of 3 equals y minus 9, 3 equals 12 minus 9. And then just double check to make sure it's true. There's nothing to do with the 3. 12 minus 9 is 3. So we do have the same value on both sides of the equation. We might have something like 7z equals 28. Now again, asking our questions here, we find our equal sign. We identify where the variable is. It's on the left side this time, 7z. What is keeping z from being alone? 7. What operation was used to attach the 7 to the z? Multiplied. So how do we get rid of it? We divide. The opposite of multiplying is dividing. I'm just going to use the fraction bar. So 7 divided by 7 cancels out, leaves us with z. We have to make sure we do exactly the same thing to the other side of the equation. 28 divided by 7 is 4. Z equals 4. Again, we can double check. Taking that original equation, instead of 7z, it's 7 times 4 to see if that equals 28. 28's by itself. We combine 7 times 4 is 28. So yes, we have the same, bless you, we have the same value on both sides of the equation. Well, it doesn't stay that simple either. We can run into something like 5x minus 2 equals 38. So here again, we find our equal sign. We identify which side the variable is on. We ask ourselves, what is keeping that x from being by itself? There's two things now. They are the 5 and the 2. The 5, of course, has been multiplied, and the 2 has been subtracted. So we have to ask ourselves what's been done to x to build this equation. Well, order of operations tells us if x were a number here, what would I have to do first? Would I multiply by 5 first, or would I subtract the 2 first? You'd multiply first. So the first thing that happened to x is it was multiplied by 5. Then the 2 was subtracted from it. Now, if you think about this, if you think about putting something together at home, whether you've put together a piece of furniture that you bought and had to assemble, put together a toy for your kids, or even maybe put together a car motor or something. You've just finished. You've just put on the last piece. If you have to take it back apart again, what's going to be the first piece you take off? The last piece you put on. The exact same thing goes for solving an equation. When we go to take it apart, we have to take off the last piece that was put on first. That would be the subtracting 2. How do we take that off? Add 2. So that minus 2 is gone, leaving us with 5x. We add 2 to the other side to get 40. Very good. 38 plus 2 is 40. Now we can go up and get rid of the times 5 by dividing by 5. So that 5's gone. X equals, we have to remember to divide the 40 by 5 as well to get 8. To double check, instead of 5x minus 2, we do 5 times 8 minus 2, just to make sure that that 8 works in place of x. That better equal 38. So 38 stays. What is 5 times 8? 40. And if we subtract 2, we get 38. So we do have the same value on both sides. So let's try 3x plus 8 equals 20. We'll do this part one more time. What was done to x? Yeah, you've got her. What was done to x to build this equation? It's been multiplied by the 3 and 8 has been added to it. To take it apart, what do we have to get rid of first? We have to get rid of the 8. So subtract 8. Very good. So the 8's gone there, leaving us with 3x. 20 minus 8 is 12. And then divide by 3. Very good. 4 equals x. We double check. Can we put 4 in there and make it work? Well, does 20 equal, instead of 3x, it's 3 times 4 plus 8? 3 times 4 is 12. 12 plus 8 is 20. So that does check out. 4 equals x, or x equals 4 is the solution to that equation. I'm going to have you guys try a couple in your notes. I'm going to have you try those two. I'm going to give you a minute. Okay, so for the first one here, 4x plus 11 equals 39. Where do we start? We subtract 11. So we have 4x equals 28, and then divide by 4. X equals 7. Okay. Sure. If you have to go back to the calculator to do the addition and division and stuff, that's fine. I mean, we all have those mental blocks. The second one over here, what do we have to do first? Add 7. So the 7's gone. We've got 18 equals 2y. And then divide by 2. So 9 equals y. Y equals 9. How many of you had both of those correct? Close to it? Okay. Any major questions on those? The next step. We can run into something like this. We identify or find our equal sign, and we identify where our variable is. And we'll notice the x appears twice, but both times are on the same side of the equation. If we think of that balanced scale, they're both on the same side of the scale. So with that in mind, can I take the 5x and 2x and push them together into one big pile? Would that change how that equation balances? No, it wouldn't change at all. So we can go ahead and push them together. What is 5x plus 2x? 7x. Now we can't forget we still have that positive 3 there, and it still equals 24. So that equation of 5x plus 3 plus 2x equals 24 just becomes 7x plus 3 equals 24. So the first step that we must do before we can start to solve any equation is simplify or combine anything we can on each side. So here we could simplify it by combining the 5x and the 2x. Now just for practice, what would we do from here? We would subtract 3, 7x equals 21, and then divide by 7. X equals 3. Similar to that, but slightly different. So you can see here we find our equal sign, and we go to identify where the variable is. X appears twice again. Unfortunately, this time it's once on each side of the equation. Can I push them together now into a big pile? No, I can't. They're not together. So before I can start to solve this, I have to get rid of one of them. I usually get rid of the smaller one. That would be the 2x. Mathematically, how do I get rid of something? I add the negative or I subtract it. So a positive 2x, I can either add a negative 2x or subtract 2x. That's gone. Leaves me with just the 24 over here. Now, exactly, if I take 2x away from one side, I have to do the exact same thing to the other side. Where can I take it from? The 5x. I have to take it from something with the same name. 5x minus 2x is 3x. And I have to remember I still have that positive 3 there. So that's the second thing we would have to do before we could start to solve an equation, as get it down to only one variable. And usually that'll mean a variable on each side. So now 3x plus 3 equals 24. How do I solve it? Subtract the 3. You could, but you'd end up equals 0 at that point. It just adds extra steps to it if you do that. Yeah. Yeah. Whatever, as long as whatever you do to one side, you can do the same, you do the same to the other. As long as you do that, the equation will always be true. It doesn't necessarily get you closer to solving it. It might be getting you further away from solving it. You may be adding onto it rather than taking it back apart. So now we have 3x equals 21. What do we do next? Divide by 3. X equals 7. Now again, just like any other equation, we could go back up here now that we got x equals 7, and we can replace x with 7. 5x would become 5 times 7 plus 3. 2x plus 24 is 2 times 7 plus 24. 5 times 7 is 35 plus 3 is 38. Over here, 2 times 7 is 14 plus 24 is 38. So we got the same value on each side. I'm going to have you guys try a couple in your notes. Have you tried those two quick, and we'll talk about them in a minute. Okay. A couple of you look like you're still working, but that's okay. Let's go ahead and see how you've done so far. So the first one here on the left, what do we have to do first? Well, before we start solving, we've got a variable on each side. Okay, we're going to combine them, get rid of one of them. Use the smaller one, and you're correct. That's the 5x. So we'll subtract the 5x. That's gone, leaving us with negative 2. On the other side, we have to subtract 5x from the 7x. 7x minus 5x is 2x, and we still have the negative 18. And then we add 18. We start to take it apart. Negative 2 plus 18 is 16. We still have 2x on the right side, and then we would divide by 2. 8 equals x, or x equals 8. Any questions on that one? Could you have subtracted the 7x? You could add the 18. It's just then, as long as you're adding or subtracting or multiplying, dividing the same thing to both sides. The key is you try to get it down, because when you multiply or divide, it gets a little more complex if you don't have it down to a single term. You can see here when we added or subtracted, I only have to add or subtract to one piece on each side. When I multiply or divide, I have to multiply or divide every digit, every piece on each side. Like here, when I divided by 2, there was only one thing on the left and only one thing on the right. So if we have it down to just one thing on each side to multiply or divide, that's easiest. I said, but as long as you're doing the same thing to both sides, you're not going to screw the equation up. You might be just getting further away from being solved or closer to it. Here, adding 18 to both sides, you actually are getting closer to solving it, but you're doing it a little out of order. It's always best to get it to the variable appearing just once before you start to take things apart. Yes. Once you have the variable only appearing once, then you can start to take apart everything else. Yeah. Whatever side the variable's on is the side you want to take apart. Like here, adding the 18 worked for this one, but if this x had been smaller, well, then you end up, you didn't want it on that side, you wanted it to stay where it was. So you added an extra step to yourself. On the right one over here, the 29 equals 2x plus 5 plus 4x. What do we do first? We combine 2x and 4x are on the same side, so we make them into 6x plus 5. And there's still 29 on the other side. And then we subtract 5. So 24 equals 6x, that 5 is gone. And then divide by 6. That 6 is gone. 4 equals x, or x equals 4. Any questions there? Well, since we're having fun with these, let's keep going. Our next step, maybe different definition of fun. 3 times, in parentheses, 5x minus 7 equals 9. Anytime we see parentheses, it should scream at us, do something here first. When we see parentheses, there's 2 questions we have to ask. Number 1 is there anything to do in the parentheses? Is there anything to do inside the parentheses here? 5x minus 7, can that be combined at all? No. So the second question, is there anything to do to the parentheses? And in this case, what's being done to the parentheses? Multiplied by the 3, very good. So we're going to use that shortcut of distributing. What is 3 times 5x? 15x. What is 3 times negative 7? Negative 21, and that still equals the 9. Now we have it down to that form, that 2-step form, so we take it apart by add 21. 15x equals 30, and then divide by 15. Good. X equals 2. Now, I get asked a lot of times at this point, well, couldn't I have just divided by 3 here and got rid of the 3 and divided the 9 by 3? In this equation, that would have worked, but it doesn't always work. So I recommend you take care of the parentheses where it's at instead of trying to do that. Let me show you what I mean. We might have 5 times 2x plus 7 plus 6 equals 81. Here, I could not just divide by the 5 to get rid of it. It wouldn't work because there's other stuff there, that's 6. So we go ahead and we're going to do the parentheses. Anything to do inside the parentheses? Yeah. That's all that I changed, was adding the 6. There's extra pieces here. Well, like I said, some people up here say, well, why can't we just divide by 3? Well, here we could have, and it would have worked. But if there's anything other than just the parentheses and that one multiple there, it won't work. We could not divide by 5 here and make this work. It would screw us up. So that's why I warn you, don't just divide out that number with the parentheses and go from there. So the parentheses, again, is there anything to do inside the parentheses? No. To the parentheses? Yes, times 5. What is 5 times 2x? 10x. And 5 times 7? Positive 35. Now we do still have that positive 6 there. Now remember, we talked about, before we start to solve things, we see if we can combine or simplify anything on each side. Here we can combine 35 and the 6 makes 41. So we've got the 10x plus 41 equals 81. Now we've took care of the parentheses. We combined with the things we could combine on each side. Is the variable down to appearing on only one side? Yes, it is. So now we're ready to solve. What would we do to solve it? Subtract 41. So 10x equals 40, and then divide by 10. X equals 4. And as always, we can go back and replace that x with 4. And we see if this works out. 2 times 4 is 8. 8 plus 7 is 15. 5 times 15 is 75. Plus 6 is 81. So we get the same value. Any questions? Okay. Well, let's step it up a notch. What's that? So let's try something like this. Just a little more difficult. We can focus on each side of this equation separately to simplify. So I'm going to start on the left side over here first. There's parentheses, so we got to look there first. What are we going to do with that parentheses? Distribute. 4 times 3x. Not everybody at once. 4 times 3x is 12x. There we go. 4 times negative 8. Negative 32. There we go. We still have the negative 2x there. Now, before we go to the other side, is there anything else we can combine or simplify on the left side? 12x and negative 2x make 10x. And we still have, of course, the negative 32. Now we've simplified the left side as much as we possibly can. So let's go to the right side. On the right side, what do we have to do? Times the 3, just distribute the 3. 3 times 2x is 6x. 3 times 1 is 3. And of course, we still have the negative 5x there. Anything else we can combine or simplify there? 6x and negative 5x make 1x or just x. And we still have the plus 3. Now, we can't simplify anything on each side. Are we ready to solve? Say no. What do we have to do first? We have to get rid of one of the, there's a variable on each side, so we have to get rid of one of them. Which one do we get rid of? the smallest, which is the x. Think of that as a 1x. So we subtracted 1x. We have to do the same on the left side. 10x minus 1x is 9x. We still have the minus 32, and it equals 3. And then, careful, here's our variable, right? So that's the side we want to take apart. Add the 32, very good. So 9x equals 35, and then divide by 9. X equals 3.88888888. 3 8/9 or 3.89, either way. Any questions? Do you want to go back to that one, or do you want to try a different one? Okay. That's a positive 9. This over here. Okay. Question. Very good question. Only what's inside the parentheses gets multiplied by the 3. So that negative 5x out there stayed negative 5x. Well, let's try another one, just for fun. What he did is when he multiplied, he did 3 times 2x is 6x, 3 times 1 is 3. He also did the 3 times that is negative 15x. Can't do that. That's outside the parentheses, so it's not multiplying. Yeah. Okay, so let's take a peek at another one. I'm going to have you guys try this one in your notes, and I will shut up and let you work on it quietly so I don't disturb you. There we go. Try that one. I'm going to pause the recording for a while. There'll be a quiz next week. It just hasn't appeared in the system yet. It just won't appear until like an hour and a half before class. So we can look at each side separately. We're going to look at the left side first here. That first, we're going to move left to right. That first set of parentheses. Is there anything I can do inside there? No, I can't. So I'm going to multiply by the 2. 2 times 5x, 10x, and 2 times negative 7, negative 14. So we finish that parentheses. The next parentheses, anything I can do inside of it? Nope, but 2 it times negative 5, you got to remember. It's the negative is going to go with that 5. So negative 5 times 3x is negative 15x. Negative 5 times negative 5, positive 25. Now I'm going to stay on the left side. What can I still combine? Perfect. 10x and negative 15x is a negative 5x. And negative 14 and positive 25 give you plus 11. Positive 11. Okay. We know what you meant. On to the right side. We're going to go left to right. First parentheses, we multiply by the 3. 3x. 3 times x is 3x. And 3 times 3 is 9. Second parentheses, is there anything we can do in there? No. So we're going to multiply by negative 2. Negative 2 times 4x, negative 8x, and negative 2 times negative 1, positive 2. What can we combine? 3x and negative 8x make negative 5x. 9 and 2 make 11. Then what? X appears on both sides, so I'm going to get rid of it. It's a negative 5x. I add 5x. Problem is they both disappear, don't they? 11 equals 11. Is that true? Yeah, it's true. 11 equals 11. So what that's saying is I can put any number in there for x, and this equation will be true. Yeah, the x has disappeared. If that ever happens, I can subtract 11, get 0 equals 0. That's still true. If I ever get that where the variables disappear, there's two possibilities. One is what we have right here. This is a true statement. 11 equals 11. So that means x can equal any number, including 0, yes. The other possibility is I might get something like 7 equals 3. That, of course, is not true. What that means is there are no solutions. There is no value I can put in there for x that would make 7 equal 3. I'll try not to do that to you too often, but I had to show that example just so it was out there. Any questions? Okay, it is 7:19, so it's time for our second break. Let's come back at 7:29. Okay, so for this last hour, we want to take a look at word problems and breaking them down. Now, I'm going to openly admit the first few that we might do here are going to be simple enough that you can look at them and know how to solve it, know how to get the answer without having to write an equation. So it can be a little bit difficult to write an equation once you already know the answer. But I'm going to ask you to be patient and go through the process, because once you see it with the simpler ones, it builds up to the more difficult ones. So something like Sam sells t-shirts for $8 each. How many t-shirts did Sam sell on a day where sales is or was, however you want to word it, $136? Now, most of you probably are reading this and saying, I'm just going to take 136 divided by 8. That's my answer. And that would be the answer. But let's think about how we would write this out. Here's a case where there is a standard concept out there that applies to this problem. And that is a price per item times the number sold equals total sales, total revenue, if you want to put it that way. So here, do I have the price? That'd be the $8 each, correct? They were $8 each. Do I know the number sold? No, I am looking for how many were sold. So that's going to be my X. Equals, I better know the total sales. That is the 136. I can only have one unknown number in these to be able to solve them. So I have that equation, 8 times X equals 136. And of course, I'm going to solve it by dividing. X is multiplied by 8, so we divide by 8. You get X equals, what was that, 17? Now you can see there, you ended up solving it by doing 136 divided by 8, which is what we had said at the beginning was the process to solve it. But we, again, wanted to practice writing out that equation. Any questions on that one? Yep, I'm going to give you just a second to finish writing her down before I move on. Okay, so if Pat saves 1/5 of each paycheck, how much was Pat's check for a week where Pat saved $72? Now, again, most of us can look at this and say, what would we do to find the answer? 72 times 5, exactly. But let's work at writing an equation for this. 1/5 of the check would be 1/5 times whatever the amount of the check is. We could write it as X, we could write it as Y, whatever variable we want to use for it. So 1/5 of Pat's check would be 1/5 times X. And of course, that is the amount saved. That equals 72, the amount saved. We're going to solve this by dividing by 1/5. Now, we learned last week that dividing by 1/5 is the same as multiplying by 5. Very good, the reciprocal. So 72 divided by 1/5, or 72 times 5, is 360. So Pat's check for that week was $360. Any questions? Now, one thing you will see here that we use the strategy of, in each of these, we have two numbers that have to represent the same amount. We just represented it in two different ways. In one way, it was a total, a dollar, a number amount, and in the other way, it was a formula. For both of these, it was that way. 1/5 times X equals 72. Up here, it was 8 times X equals 136. And that is one of the possibilities we look for in these. The other possibilities, so that's A equals B, that's one possibility. We have two things that equal each other. The other possibilities, well, one of them would be those two things have to add up to equal a total. We'll look at some of those examples in a little bit. The other is those two things subtract to make a difference. So let's look at an example of that. Let's say Peyton sells 4 more items. Now, let's see, I'm gonna be careful here. Peyton sells 4 items. Peyton and Alex sold a total of 15 items. How many did Alex sell? This is an example of the second type here. We're looking at a total. And this problem even has that nice word in there, total. Peyton sales plus Alex sales equals a total of some sort. Do we know Peyton's sales? Yeah, 4 items. Do we know Alex's sales? No, that's what we're looking for. I can call that A or X or whatever I want to call it. Do I know the total? 15. And now we can solve that. Subtracting 4 from both sides, A equals 11. What do you think? An example of that third type, we could have Kim owns 7 more let's put dolls than Kelly. Kelly owns 12 dolls. How many does Kim own? How many does, no, careful. So what we have here is a difference. Kim, of course but I have to put the whole name in here. I can't just do K minus K. Kim minus Kelly has to equal 7. Kim owns more, so that makes Kim the larger number. As always, the bigger minus the smaller gives us the difference. Do I know the number that Kim owns? I'm looking for how many Kim owns. I'm going to make that X. Minus Kelly is 12. The difference is 7, so it has to equal 7. So I'm going to solve this by just adding 12. X equals 19, so Kim has 19. Now, those are all very simplistic word problems. And because they're so simple, it's often more difficult to write an equation for them because your mind wants to go just to calculating the answer and not writing it out with a formula. So let's look at some more difficult ones. We might have, I'm going to stick with sales here. Pete sells 4 more items than Sam. They sell a total of 42 items. How many did each sell? Now I'm going to pause for a second before I start solving this so that you guys can get it written down. Now, it often helps me on problems like this to kind of map it out a little bit. I have 2 items here that I'm trying to describe. I have Pete's sales and Sam's sales. Do I know the number for either one of them? No, I don't. I don't know the total. I do know that Pete sold 4 more. And so in a problem like this where I have 2 things I'm looking for, I look to see if one of them can be calculated from the other. Pete selling 4 more means if I know Sam's, I can do what to get Pete's? Add 4. But in order to find Pete's, I need to know Sam's first, right? So I'm going to let Sam's sales be X, because that's the one I have to know first. If I know Sam's, I do what to get Pete's again? Add 4, so X plus 4. So now there's a total of 42. So X plus 4, that's Pete's sales, plus Sam's sales, which is X, adds up to 42. And now to solve this, I have to combine. The variable appears twice on the left side there. What's X plus X? Yes, think of it as 1X plus 1X is 2X. Plus 4 equals 42. And then subtract the 4. 2X equals 38. And then divide by 2, X equals, careful, 19. Now we have to make sure we answer the question. It's very tempting to get to this point. We solve the equation, we have X equals 19 and think, we're done, we've accomplished it, we solved it. But we have to make sure we've answered the question. The question is, how many did each sell? Well, what does X represent? Sam. That's one of the reasons why I map it out like this, is so once I've solved the equation, I know what the variable is telling me. This is telling me very clearly X represents Sam, so Sam was 19. And now also because I have this written out, I can find Pete. It's X plus 4, so 19 plus 4 is 23. Any questions? What's that? Yes. It is just, I mean, sure you can save a few seconds by skipping it, but at the end it saves you a lot of confusion by having it written down. So Pat sells 4 times as many items as Chris. They sell a total of 85 items. How many did each sell? Very similar problem, but slightly different. Again, I'm going to pause for a second here where you guys finish writing it out if you need to. Okay, so once again, we have 2 things we're looking for. We're looking for Pat's number of items Pat sold and the number of items that Chris sold. Is one of them calculated from the other? Yeah, Pat sold 4 times as many as Chris. So which one do I have to know first? If I know Chris, I can calculate Pat's. So which one becomes our variable? Chris's. If Chris is X, Pat's would be 4X, or 4 times that. So now that I have that, I can go ahead and write an equation. Are these added? Are they subtracted? How are they related? Total of perfect. Pat plus Chris equals 85. So 4X plus X equals 85. And yes, we treat that as 1X. So that combines to be 5X equals 85. Next step is divide by 5. So X is 17. And then, so that tells us Chris sold 17 items. Pat is going to be 4 times 17, or 68 items. It really is helpful. And as we get into more complicated problems, it continues to be helpful. So let's keep going with this idea here. Let's say Tim sells 3 times as many items as Phil. Tim sells 28 items more. 28 more items, I should say, than Phil. Once again, how many did each sell? So once again, we're looking for the number sold. Is one of them, we have 2 amounts to find, is one of them calculated from the other? Yes. Tim's sales is 3 times that of Phil's. So Tim's sales is referenced from Phil's, is the technical way of writing that. So which one do I need to know first? Phil. So Phil is X. And if I know Phil's, how do I find Tim's? 3 times that, so 3x. So we know that those two add up to, they don't add up in this one. What's the difference there? Tim sold 28 more. That means we're doing a difference. Tim's minus Phil's is 28. So we have 3x minus x equals 28. We put in a 1x there. So 3x minus 1x is 2x equals 28. And then divide by 2. X equals 14. And again, x was Phil, so Phil is 14. Tim is 3 times 14, or 42. Now, there is an alternative way we could have written this equation, saying that Tim sold 28 more than Phil. We could say Tim equals Phil plus 28. Notice, though, that when we go to solve that, what's the first thing we're going to do? That we're going to subtract x from each side. We still get 2x equals 28. We end up at the same equation. It's just starting in a slightly different point. There are all sorts of formulas that we could use. Some of our problems run into set formulas. One of those problems might be interest. Simple interest is equal to principal times rate times time. And I might ask you to find the principal on a loan that we're just going to, for lack of a better word, charges $120 interest for 1 month at 8%. So here, we know the interest, that is the $120. Do we know P, the principal? No, that's what we're trying to find. The rate is the 8%. We have to write it as a decimal, 0.08. T is time. Now, I didn't say this yet, but time is always expressed in years. So 1 month is 1/12 of a year. So to solve this, remember our first thing we have to do is combine things that we can on one side of an equation. So the 120 won't change. This is going to be P times. Now when I put this in my calculator, 0.08 times 1/12. I don't have to use the fraction function, by the way. I can just 0.08 times 1 divided by 12. That does the same thing. I get 0.0066666666. This rounds it off to 7 at the end, but it really is 6 going on forever, isn't it? That means the calculator has rounded this number. That means if I write it down, and try to type it back in, it's going to be a rounded number, which means I've introduced an error to it. Your calculators all have this function. Usually it's a second function. If it's on the Texas Instruments, it's down by the equal sign, and it's above one of the keys that says ANS. On the Sharp and the Casios, it's actually usually right on one of the keys. It says ANS. What that key is that's telling the calculator to use the previous answer. So if we're solving this equation here, I just type this in to get that 0.00666667. What's my next step to solve this? I have to divide by that 0.00666667, right? So what I'm going to do in my calculator is I'm going to type in 120. Now notice I did not hit clear. That's important that I don't do that. I type in 120 divided by, and instead of typing in that 0.0066666667, I'm going to do second. And notice my ANS key is down here. It's the second function above my negative key. It says ANS. .08 just times 1 divided by 12. 1/12, you're multiplying by 1/12. So it's 0.08. You can either use the fraction key, 1/12, or you can do just times 1 divided by 12. We'll do the same thing. The ABC key, 1 ABC 12. Yep. So it might give you 2 over 300. Yeah. So I do that, and it's going to spit out $18,000. So the principal is $18,000. Some of you kind of flinched a little bit, gasped a little when I said $120 interest for a month. If you have poor credit rating and you're buying a more expensive car, 8% interest is not uncommon. It is possible to be paying $120 a month in interest. That's the importance of. Does yours not work? Okay. So you've got the 0.08, right? You do the times 1 ABC 12. That 2 over 300. Now you're going to leave that. Now you're going to type in the 120 divided by. And then do you have an answer key on there somewhere? Yep. So hit that. Then hit equals. Okay. Okay. Now let's move on to some more complex word problems. Let's talk about Pat. Pat sells t-shirts. Oh, I can't spell tonight. Sells t-shirts for, let's do $12 each. And, let's do hats for $20 each. What's that? You ever go to an event and buy a hat there? Yeah. Yeah. So anyway, Pat sells 4 times as many t-shirts. Wow, I did it again. I told you once I screw something up, I do it for the rest of the day. As many t-shirts as hats. For a total of $880. That's not going to work. Let me try that again. How about $680? How many of each did Pat sell? So now instead of 2 different people, we have 2 different items. We have the t-shirts and we have the hats. Now we're still concerned with the number sold. So we have 2 different items we're trying to find. There are 2 different numbers, the number of t-shirts and the number of hats. Is one of them calculated from the other? Yes. Pat sells 4 times as many t-shirts as hats. So which one do we have to know first? We have to know the hats. And if we know the hats, we calculate the t-shirts by doing what? Times 4, so 4x. However, we're not given the total number sold, we're given total dollar amount. So we have to convert those numbers, the numbers sold, into dollars. Now, in a previous problem, we had that dollar sales or revenue is equal to the price times the number sold. That equals our dollar sales or our revenue. So the dollar sales for t-shirts is the price times the number sold. Well, what's the price? $12 for t-shirts. So it's 12 times the number sold is 4x. So 12 times 4x is 48x for the t-shirts. For hats, what's the price? 20. How many were sold? X, right? So 20 times x is 20x for the hats. So that is now dollar amounts. Those 2 dollar amounts, 48x is the dollar amount from t-shirts, plus 20x is the dollar amount from hats, has to add up to $680. What do we do next? Combine. What is 48x plus 20x? 68x. Still equals 680. And then divide by 68. X equals 10. All done? No, what do we have to do? Yeah, we have to answer the question. X equals 10, that is how many hats were sold. We still need to know the t-shirts. 4x is 4 times 10. That's 40 t-shirts sold. What do you think? I'm going to show you one more example. And then I think you guys have suffered enough for one night. Pat still sells t-shirts for $12 each and hats for $20 each. Pat sells a total of 50 items for a total of $680. How many of each were sold? Now, in the surface, this looks like the same problem, and it is very, very similar, but there's a very, very important difference here. We are still looking at t-shirts and hats. And one of the first things we're looking at is the number sold. Do we know how many of either one of them is sold? No. Is one of them calculated from the other? It doesn't say that one is a certain amount more or that one is so many times the other, but it does say that there's a total of 50 items. The tricky part here is that total of 50 items does not imply that either one of them has to be known first, does it? All the other ones we've done, it says A is 3 times B, so we have to know B first. Or A is 7 more than B, so we had to know B first. Here, it doesn't matter which one we know first. So somebody pick one, t-shirts or hats? T-shirts, so t-shirts gets to be X. Well, if we know how many t-shirts, how would we find how many hats? Well, we can't use we don't know how to use a second variable, but we can define it in terms of the number of t-shirts. Think of it this way. We have that total of 50 items here. If I told you that I sold 20 t-shirts, how many hats would we have sold? 30. So 50 minus the 20 gives us the 30, right? Well, we don't know the number of t-shirts, so instead of 50 minus 20, it'll be 50 minus X. You had the right idea, it's just backwards. Since there's 50 total, we subtract the number of t-shirts, which is X. That has to be the number of hats. Now I'm going to pause there. Any questions as to where that 50 minus X came from? Okay. So now we still have to get the dollar amount sold because we have the total dollars of 680. The dollar sales is still the price times the number sold. So for t-shirts, it's still $12 each times X, which is just 12X. For hats, it's $20 each times 50 minus X. We're going to have to multiply. What is 20 times 50? 1,000. 20 times negative X. Negative 20X. Those two numbers have to add up to the total sales of 680. So I've got 12X plus 1,000 minus 20X equals 680. Now the X appears twice. What do we have to do? Combine 12X and negative 20X make negative 8X plus 1,000 equals 680. Now we have to try to get X by itself. What's the first thing we're going to do? Perfect. We subtract 1,000. That 1,000 is gone, leaving us with negative 8X. 680 minus 1,000 is a negative 320. And then divide by negative 8. X equals negative 320 divided by negative 8. 40. Negative divided by negative is a positive, so it is 40. Now we still have to make sure we go back and answer our question. Now that we have that x equals 40, we go back up here. X was the number of t-shirts. There's 40 t-shirts. Hats is 50 minus x. So 50 minus 40 is 10 hats. What do you think? It'll take a while to get used to these. Okay, there is a new quiz. That would be quiz number 1. It actually opened up, I think at 4 o'clock tonight it opened up. That is due tomorrow, so that'll be Thursday by 11:59 p.m. Now remember, so you've got all day tomorrow, or you can do it tonight. You do have 2 attempts at that. There are none of those hints, none of those, show me an example or anything like that. So make sure you're very comfortable with the homework. This quiz will be the same types of questions as the homework you did from last week. So if you're not really sure about it, go back and review some. What's that? I'm not really sure. Is there 8 questions? I was gonna say, I know I was trying to be nice on this one. You get 2 attempts, but that's not 2 attempts per question. You have to do the whole quiz. You can submit it, and then it'll let you see what you got wrong. You can review those and try again. I would suggest you do your first attempt early, because I have students all the time that they'll wait till like 10 o'clock tomorrow night. They'll do their first attempt. They get a couple wrong. They go to study. They try to take it a second time, and it hits 11:59 and it cuts them off. So make sure you give yourself time if you want to redo it. The system automatically takes the highest score. So unless you get a perfect score the first attempt, there's no reason not to do it a second time. Also, there will be a new homework. That'll be homework 2 that is due for next Wednesday. Sure. Yeah, none of my grades should be posted yet. If you click on the grade book in Blackboard, it won't even show any assignments right now. Yeah, it's in my math lab. I just haven't brought it over to Blackboard. I have to manually transfer them to Blackboard. Okay, you guys have a great week.